Welcome. In this video we will see an exercise from paper 3, Discrete Mathematics from IB High Level Mathematics. The year is 2015 and this is exercise 2. So let's read the question. It says the graph K2.2 is a complete bipartite graph whose vertex set is a disjoint union of two subsets each of order 2. Of course, you probably have seen it before. When we're talking about graphs of this type, we have something like that. We have a set of vertices here, another set of vertices here, and the only edges that are allowed are those that connect vertices that belong to different sets. So let's say that here I have set A, here I have set B, and it is absolutely illegal to connect with an edge two vertices that belong to the same set. Now, when we're talking, that's the definition of a bipartite graph. When we're talking about a complete bipartite graph, such as K2.2, we have something like that. We have two vertices from the one side to the one set, two vertices to the other side, and we draw all the possible edges, as long as the graph, of course, remains simple and bipartite. So we have these edges and these edges here. So this is K2.2. Just to make sure that we get it, this one is K2.3. Fine. So the first question says, draw K2.2 as a planar graph. And the big question here is K2.2 a planar graph? Of course it is, because I could just draw it like this. I could take this edge, this vertex, and put it here. So I will take this and I will just draw it here. So I will have something like that. If this is 1, 2, let's name them 3 and 4. I'm going to have something like that. 1, 2. I will draw the vertex 3 over here, the vertex 4 over here, and of course you can see that this graph is exactly the same with this graph. I mean, 1, 2, 1, 2, here we go, 2, 3, 2, 3 here, this edge 2, 3 here, 3, 4 over here, and 1, 4 over here. So the first question is very simple. I just have to draw this beautiful square. So let's see now B. It says draw a spanning tree for K2.2. Does K2.2 have a spanning tree? The answer is yes, because it is a connected graph. It's a connected graph. So let's draw again K2.2 to here, to here. I have something like that. So let's say that a spanning tree is maybe this one, right? Or maybe we could say that a spanning tree is this one. It has to be a tree. It must have no circles. It has to be connected, and it has to contain all the vertices of the initial graph. That's what spanning tree means. So a very nice spanning tree this one, a very nice spanning tree this one, and we're fine. And let's go to C. It says draw the graph of the complement of K2.2. Well, as you probably remember, the complement of each graph has exactly the same vertices, but it has all the edges that the initial graph does not have. So let's make a small example here. If this is my initial graph, well, the complement is going to look like that. It will have exactly the same vertices, but it will have the edges that are not contained in the initial graph. It will have the edges that if they were contained in the initial graph G would be a complete graph. So I will have this, and this edge here. You see, if I had the red edges on this graph, it would be K4, a complete graph. Very well. So that's an example in order to remember how do we draw in general the complement of any graph. And now let's take a look at it. It says draw the graph of the complement of K2.2. Well, my initial graph looks like that. It's the fourth time that I'm drawing it. Okay, so how, okay, that's K2.2. How will K2.2 bar will look like? How does the complement of K2.2 looks like? I will have exactly the same vertices, but I will have all the edges that are not contained in the initial graph. Side note, both G and the complement of G are considered to be simple graphs. All this this definition of the definition of the complete graph stands only if the graphs that we're talking about are simple. So let's see, in the complement of K2.2, I will have only this edge here and this edge here. In general, we must keep in mind, and we're going to use this result at D. In general, if you have Kn point M, well, the complement of that is a clique of order n, a complete graph with n vertices. And over here we'll have a complete graph with m vertices. And none of these edges will appear because all of these edges, all of these are contained in the initial graph. So we have to keep in mind that the complement of that looks like that. For example, if we took the complement, let's take here, if we had K2.3, well, the complement of that looks like this. It is absolutely illegal to put at the complement any edge that connects vertices from this set with vertices of this set. And since at the initial graph none of these edges exist, I mean the edges that connect vertices that are in the same set do not exist, well, in the complement all these edges will appear. So bottom line here, the complement of K2.2 looks like that, and that's it. So let's go now to D. It says, show that the complement of any complete bipartite graph does not possess a spanning tree. Does not possess a spanning tree. Well, in general, a graph G possesses a spanning tree if and only if it is connected. A spanning tree is a tree that contains all the vertices of the graph. So, in order to show that the complement of any complete bipartite graph does not possess a spanning tree, I just have to explain why the complement of any completely bipartite graph is not connected. It is not connected. And I think that we have already given the answer to this question. Let's say it again once more. Well, at Kn point M, we have a set A that contains n vertices and a set B that contains M vertices. At the initial graph, each vertex that belongs here gets connected with an edge with every vertex that lives here. All right. And if two vertices belong to the same set, they are not connected with an edge. So at the complement, all of these vertices are illegal. There will be no all of these edges. Sorry, all of these edges are illegal. There will be no edge at the complement that will connect a vertex from A to a vertex from B, and all of these vertices will connect. So I will have a click, a complete graph. All of these vertices will connect with an edge, so we'll have a complete graph. So that explains why the fact that I will have a complete graph does not explain it. But anyway, the main thing here is that these edges here are illegal, and there is no way at the complement to have an edge or a path that connects a vertex from set A to a vertex from set B. So the complement of any bipartite, complete bipartite graph is not connected, and therefore it does not have a spanning tree. It does not possess a spanning tree. It is a very easy question. I mean, a very easy exercise. If someone remembers the definitions, some basic definitions, it's quite easy for any type of help or for anything else that you might need, a question or a specific exercise that maybe you need some help to that. You can always contact me through this email. Thanks for watching and good luck.